Hello everyone. I'm Luming Wang from Institute of Computing Technology, Chinese Academy of Sciences. Today I will introduce our work, Asynchronous Memory Access Unit for General Purpose Processors. Nowadays, the prevalence of in-memory computing applications, such as in-memory databases, graph processing, and big data applications, has caused massive growth in memory demand. To meet the growing demand for memory, file memory is introduced into data centers. File memory include non-DRAM memory technologies such as non-volatile memory and emerging interconnect techniques that provide memory-like semantics. Although file memory provides higher capacity and larger aggregated bandwidth than traditional memory, its access latency is higher than that of DRAM. Moreover, it is reasonable for future servers to employ multiple file memory techniques with completely different performance characteristics at the same time. This makes the access latency of file memory widely distributed. Thus, file memory leaves a challenge for CPU to fully utilize the resources. Modern processors had long access latency by exploiting memory-level parallelism. The out-of-order execution mechanisms and non-blocking cache has implicitly issued multiple memory requests simultaneously. However, the maximum number of in-flight memory requests is restricted by critical hardware resources such as reorder buffer and mean status hold registers. In file memory scenario, a long latency load store instructions will occupy the ROB and the MSHR for a longer time. Reorder buffer generally has only a few hundred items, where the MSHR that maintains outstanding memory access has only 42 items in the Intel Golden 48 48 items in the Intel Golden Core. Such few resources are not enough to boost MLP and will cause CPU stalls. As an example, let's say a 2 GHz processor is faced with a 1 microsecond latency, which is equivalent to 2,000 cycles. To avoid pipeline stalls, thousands of ROB and MSHR entries are needed, which is unachievable. We argue that the load store instructions synchronized semantics are the key obstacle that prevents more memory level parallelism. Due to the synchronized semantic of traditional load store instructions, a memory access operation will hold critical hardware resources for a long time. Thus, we propose an asynchronous memory access unit, which provides asynchronous semantics for load store. AMU is similar to the vector process unit in general purpose processors. It provides asynchronous memory access instructions. Applications can employ these instructions to accelerate file memory access. We split the memory operation into two instructions. One is for sending the request and the other is for getting the response. Thus, critical resources can be released in a short time. There are two design challenges of AMU. First, converting traditional synchronous access to asynchronous access can place pressure on the registers. A large amount of storage space is needed for holding the data of asynchronous memory requests. Second, the number of MSHRs is not enough for tracking the states of in-flight asynchronous memory request. To hold the status of asynchronous memory requests, large amounts of space are needed. To address these challenges, we propose to dynamically divide a portion of the cache into scratchpad memory. The SPM will be used to replace the role of physical register files and the MSHRs. As the size of SPM is much larger than the size of the registers, it will be easier to support a large number of concurrent memory access requests. The SPM will be divided into two areas, data area and the metadata area. The data area is fully managed by software. It holds the data of asynchronous memory operations. The metadata area is managed by AMU. It tracks the states of in-flight memory operations. There are three core instructions of AMU. These instructions enable the most basic asynchronous memory access. A-load and A-store instructions can invoke a data movement request between SPM and memory. Once the request is successfully invoked, a request ID is allocated for tracking it. Applications can use the getFin instructions to obtain a completed request's ID. Several configuration registers are proposed for invoking complex asynchronous memory access requests. Here is a basic example of asynchronous memory access. First, we configure the AMU to set the memory access granularity and maximum concurrency. Next, we allocate a block of SPM, initiating an A-load or A-store request. Then the program can handle other things and use getFin to check if the request is finished when needed. Finally, programs can access SPM through standard load store to obtain the memory data. To efficiently implement support for asynchronous memory access instructions, the AMU has two design considerations. First, we design an efficient request ID management mechanism that supports out-of-order and speculation mechanisms. Second, as SPM doesn't provide consistency checking as MSHRs, this work relies on software to handle the consistency. For multi-thread applications, they generally adhere to the data risk-free model. Thus, normal data operations can be safely reordered as long as they do not cross the synchronization point, such as atomic instructions and locks. For other programs, it is possible to use a combination of hardware and software solution to handle the consistent problem of asynchronous access to file memory. To demonstrate the concepts of AMU, an early simulator prototype has been built. We modified Gem5 to implement a cycle-accurate model of AMU and evaluated it by running random access benchmark from HPCC. We manually inserted asynchronous memory access instructions. The file memory latency is set to several different values from 100 nanoseconds to 5 microseconds. AMU performs similarly across different configurations, where the performance of baseline drops rapidly when the access latency increases. The results shows that AMU can better tolerate a large range of access latency.